All right, so we're starting chapter 13 with section 13.1. We're going to do an introduction to vector valued functions, otherwise known as vector functions, and space curves. So this chapter will bring up some old topics that you learned about in Calc 1 and Calc 2, like position, velocity, and acceleration. We're going to deal with them in the context of vectors. We'll talk about things like curvature. We'll talk about different components of acceleration that really define these space curves. So there's some cool stuff in this chapter that goes beyond what you learned in the past. So let's start with the definition. A vector valued function, sometimes just called a vector function. It's a function whose input is a real number and whose output is a vector. Okay, so the domain is the set of real numbers. The range is a set of vectors. So in function notation, it's a function. It takes in a real number and it spits out. I'm just going to put kind of loose notation here. Your output would be some two-dimensional or some three-dimensional vector is what we're going to be dealing with. We are going to typically define our vector to be R, and we'll see that's typically what we use for a position vector if we're working with a physics context. R is typically what we'll use for our position vector. You'll notice the input is some parameter t, and it outputs a vector. In this case, it has three components. Each of these individual functions that you see in the position of x, y, and z are what we call the component functions of R. Okay, so they're just some real valued functions that you would have learned about in the past. One thing you should be able to do with a vector valued function is find the domain. What are the restrictions on the parameter t that we can use to define that vector valued function? And what you do is you look at the domain of each of the individual component functions and you find the intersection of those individual domains. The intersection of the domains of those component functions is your domain for that vector valued function. So let's take a look at an example. Here I have the vector valued function made up of the components natural log of the absolute value of t minus 1. So I'm going to label these one by one. So my f of t in this case is natural log of the absolute value of t minus 1. I kind of do a little squiggle. G of t, the second component, is e to the t. And then h of t, my third component for z, is the square root of t. And so I'm just going to look at the individual domains of f, g, and h and figure out where they intersect. The natural log function, let's take a look at f. If you remember, the natural log function can only take in inputs that are greater than or equal to 0. So if I'm looking at the argument of the natural log function, what I put into it needs to be at least 0. So in this case, I'm putting in the absolute value of t minus 1. That means the absolute value of t minus 1 needs to be greater than or equal to 0. Well, it can't be negative. It's always going to be at least, it's going to always, yeah, it can't, the absolute value function can't be negative. So we don't have to worry about that highlighted piece being negative. At the very best, it'll be positive, but it could be 0. So I have to look at the case where what value of t would make the absolute value of t minus 1 equal to 0. We don't want that to happen. That value won't be allowed to be in the domain. And in this case, that would be when t is equal to 1. So we do not want t to equal 1 in this case. Otherwise, we're taking the natural log of 0, and that's a problem, right? That's gonna become negative infinity, and that's just a problem. So second component, g of t equals e to the t. No restrictions on the domain in that case. T can be any real number that we want. Exponential function has no domain restrictions. And the square root function for h, what's under the radical has to be greater than or equal to 0. We can't take the square root of a negative number. We are not dealing with complex numbers in this class. So we want what's underneath. T is going to have to be greater than or equal to 0. Well, if I look at the intersection of all three of those, has to be a real number. Okay, that's pretty broad. Has to be greater than or equal to 0, but can't equal 1. So really, we're looking at all of the values greater than or equal to 0, but we have to exclude t equals 1. So I'm going to put my answer in interval notation. My domain, if I look at the intersection of these three pieces, would be everything from 0, including 0, to 1, excluding 1. So I'm going to put a parenthesis. Union picks up again, excluding 1, and then according to our rules, any other number greater than or equal to 0 can work. So we're going to end by going all the way to infinity. Okay. So this would be my domain for the entire vector valued function. Okay. Okay. Now we want to kind of we're interested in graphing these vector valued functions and seeing what that produces. And so let's suppose that f, g, and h are continuous real valued functions on some interval, I. Then the set C of all points x, y, z in space given by these three parametric equations, x equals f of t, y equals g of t, and z equals h of t, letting t vary throughout that interval. This is what is called a space curve. And you've done this in the past when you only had an x and y component. When you're dealing with this in 2 dimensions, this was parametric equations that you looked at in pre-calc. You were graphing plane curves. You were restricted to a 2-dimensional plane, and you looked at what those parametric equations graphed on that plane. It's the same idea, except now we're dealing with 3 dimensions. So this is called a space curve. You're dealing with 3-dimensional space. It's a path. All you're doing is traversing a path, and you're looking at how that path is traced as the parameter value increases or decreases. So just like you learned with parametric equations, the orientation matters. Right? There's going to be a specified orientation, a direction that curve has to follow. Okay? So the individual functions are called parametric equations of C, and T is called the parameter. This is a set of parametric equations, okay? And it produces a space curve, is what we call the graph. So any continuous vector function R defines some space curve C. And really, how do we get this? Well, we trace out the tip of that moving vector R of t. So in my picture here, I'm going to outline this in green. This would be my moving vector R of t. And as I let that green vector move from point to point on the pink curve, you end up traversing that pink curve. So maybe the vector starts out here, and then a few seconds later, now it's here. Well, it's moving along this curve. And so this entire, if you were to pretend that green tip continued to move forever and ever along this curve, according to this orientation, you would get the whole space curve. It's much easier to visualize if you actually animate it. So we have the wonderful CalcPlot 3D I'm going to show you here. There it is. And I've created a specific space curve. This is a real popular one we're going to look at. This is what's called a helix. It looks like a slinky. We're actually going to graph one in a few minutes here. But I just I picked one that you can see on the screen. I let my parameter vary from -10 to 10. I'm actually going to start with -100 to 100 to show you it moving very fast. And I'm going to show you the vector valued function here, or the tip of the vector. So you're going to see 3 arrows. I believe one is black, one is green, and one is blue. Focus on the blue one. We'll talk about the other 2 vectors that you see in a couple sections from now. But the one in blue is the one you want to focus on. That's the one that's going to be tracing out to the tip of this space curve that you see and really showing how it's designed. So trace, animate, and it's moving very quick. So just focus on the blue one. You'll notice the vector starts at the origin, and it's basically tracing out the shape that you see. Okay? As t increases, we continue to move in the positive y direction, and we get this circular helix pattern, this slinky type spiral pattern. Let's slow it down a little bit. If I change the parameter from, let's go -10 to 10, I'm going to let trace t out, t equals 10. It slows down a little bit so you can really see that spiral pattern happening second by second. So think of t as time. As time passes, as the parameter value of t increases, we start tracing out this space curve, circle by circle, spiral by spiral. So you get the idea. Tracing out that vector is what's creating this space curve. And you can play around with different values of t. Pause the video if you want to see what I inputted for x, y, and t, or x, y, and z. All I did from the menu, I dropped down and I inserted a space curve, r of t. Okay, so that's what you would want to use from the pull-down menu if you want to try this on your own. Look at my component functions. You can play around with it. What happens if you change x, y, and z? You'll get different space curves. But that's the idea. Okay, let's do a plane curve to start with here. Let's sketch the curve whose vector equation is given by r of t equals 2 cosine ti minus 3 sine t j. So no z component for this one. So we're just looking at the xy plane from 0 to 2 pi. Okay. And so this is your typical parametric equations that you would have looked at in pre-calc or last year in Calc 1, Calc 2. I'm going to write this in component form. R of t equals 2 cosine t comma negative 3 sine t. And you might know what this is from your previous study of parametrics. There's your x of t and there's your y of t component functions. So I'm going to write those down. X of t is 2 cosine t, and y of t is negative 3 sine t. Now, when the coefficients are the same, using cosines and sines parametrically typically produces a circle. If you remember this from the past. When we place different coefficients in front, let's see what we get. Okay. So in this case, I'm just going to pick my favorite values for sine and cosine, which are the values right on the unit circle. So I'm going to do this by making a table. If I don't know what it looks like, making a table is the best way to go. So I'm just going to pick the classic 0, pi over 2, pi, 3 pi over 2, and 2 pi. And I'm going to look at the ordered pairs that come out, and I'm going to place them on the graph. So if I put in t equals 0, I get 2. And if I put in t equals 0 for y, I get negative 3 times sine of 0, so I get 0. So my first point on the curve is at 2, 0. As t increases, remember the direction matters, so we're going to have to draw an arrow in the direction of where we end up next. Plugging in pi over 2, 2 times the cosine of pi over 2 would be 2 times 0, so I end up at 0. Negative 3 times the sine of pi over 2, negative 3 times 1 would be negative 3. So the next place I go is 0, negative 3. Okay. At pi, 2 times the cosine of pi would give me negative 2 for x. Negative 3 times the sine of pi would give me 0 for y. So the next ordered pair I reach is negative 2, 0. So it looks like we're going down into quadrant 4. We end up touching the negative y-axis, and then we're back to, so far, if I can graph this properly. Here's what we've got so far. If I trace the arrows as the parameter value increases, looks like think of it as like a particle. A particle moving along that curve would be moving towards the negative y-axis and then moving towards the negative x-axis. Now let's see how it finishes. At 3 pi over 2, if we plug in 3 pi over 2, we end up with negative 2. Oh, no, we don't. We end up with 0. And if we plug in 3 pi over 2 for y, we end up with negative 3 times negative 1 would be positive 3. So now we're up at the 0.03 on the positive y-axis. So now it looks like I'm kind of making the curve as I go here. Specifying the direction. Now I've moved my way into quadrant 2, up, up, up to the positive y-axis, and you can probably predict what's going to happen here. We plug in 2 pi, we're going to end up back where we started at 2, 0. So it makes an ellipse. Whenever you're using sines and cosines for your component functions and you have different coefficients, you're going to get an ellipse traced out. The fact that one of the coefficients is negative is why we ended up going in a clockwise pattern. Had that coefficient been positive, we would have moved in a counterclockwise pattern. So that's where the orientation matters, and you got to specify that when you graph these. Okay, so we get an ellipse. If you're not sure what it's going to look like, make a table of values, and you'll get some intuition for what your picture should look like. Okay, let's increase the dimension. We're dealing with multivariable calculus. So let's see what a space curve would look like. I'm going to add a z component. This is similar to the one that I traced out on CalcPlot 3D before. My x component is cosine. My y component is sine. So that should make you think right away, before I even look at the z component, okay, x of t is equal to cosine of t and y of t is equal to sine of t. That would make me think that at least in the xy plane, I'm going to get some type of circle. So this should right away make you think, okay, something is going to be circular about this because I'm using sines and cosines. Then we look at the z component. As this space curve, or as this vector valued function moves up and down, it's moving at this linear rate. Okay? According to this z function, z of t is equal to t. So it should make you think, okay, maybe we're going to get some type of circles moving up into the air. So just some things to notice. Okay, notice that x squared plus y squared, which would give me cosine squared t plus y, or sine squared t, that's a Pythagorean identity, that's equal to 1, right? So one thing I notice is that in the xy plane, I get x squared plus y squared is equal to 1. Okay? And that circle is going to essentially spiral up into the air as we increase the value of the parameter t. As z gets bigger, we're going to end up getting this spiral type shape. That circle is going to continue to grow and grow into the air. So this curve, think about what is this in 3 dimensions. X squared plus y squared equals 1. You remember from our previous conversations, that's a circular cylinder with a radius of 1. So that's going to create the basic outline of our shape. So I'm going to sketch this so you can see it. Here's our basic, this is not the space curve, but this is what the space curve is going to end up lying on. It's going to be moving along kind of the perimeter of this cylinder, along the exterior, that surface area of that cylinder. And so this curve lies on that circular cylinder. And we'll make a table so we can kind of see where the points are going to lie. It lies on the circular cylinder, x squared plus y squared is equal to 1. So let's make a table and see where it goes. I'm going to make the table probably off to the right here. So I'm going to make a t column, an x column, a y column, and a z column. Okay. I'm going to pick the same, since I'm dealing with trig functions, I'm going to pick the same values I did for this, the plane curve we did in the last example. 0, pi over 2, pi. You can pick the pi over 4s and the pi over 6s if you want more points, but this will do the trick to give us a basic sketch. And then I'm going to put it on Calcplot 3D so you can see it a little bit better. 3 pi over 2 and 2 pi. Okay, so if I put 0 in, I'm going to speed this up and just kind of fill out the table. You're going to get 1, 0, 0. Look back at your unit circle if you need some recap. Then I'm going to get 0, 1, pi over 2, negative 1, 0, pi, 0, negative 1, 3 pi over 2. And then if I put 2 pi into this, I end up at 1, 0. I'm not back at 1, 0, 0, right? If I was just working with a plane curve, I would end up getting that circular or elliptical pattern. I'd be back where I started. But the height has changed, right? Now we have a z component, so I actually am going to be at a different height than I began. And that's the main difference here is here you're in the xy plane. Now you're up in the air, 2 pi units up in the air. So let's plot these and actually trace out this space curve. So I'm going to start at 1, 0, 0. So I guess maybe I should actually make my picture just a little more accurate so that the green make the size of this just a little different. There we go. It's actually a slightly smaller cylinder than I drew. Let's do this a little bit more accurately. Okay, so there's my cylinder. Notice I'm not outlining it in a solid color because that is not the graph that we're graphing. That's just going to be where it moves along. So it starts at 1, 0, 0. Okay. And then as the parameter value increases, think of it as a particle. Once time reaches pi over 2, we're at 0, 1. So we would be here, but then we're up in the air pi over 2 units. And so we're roughly about here. Okay. So we've moved. Kind of like, okay, there's so far where we're at. Next up, at pi, we are at negative 1, 0, pi. So now we're at, we graph this, we're at negative 1, 0, and then we're up in the air about here now. Okay. A little bit like 3.14 units up in the air. And so this is really what it's doing. We could plot all the intermediate points in between, but we're continuing to get this slinky spiral pattern that's taking us from point to point. Finally, I end up back at 1, 0. So I'd be back here, but now I'm at a height of 2 pi units up in the air. So we're way up here. So this is, maybe I should scale this down in size so we can see it. Yeah, it's okay. But we would be way up here, right? So this would end up continuing this height up here would be essentially your 2 pi, your 6.28, but it's going to be the x and y coordinates going to be 1 and 0. So we end up continuing. It's growing at this linear rate. I'll erase this to keep my slinky going. There's our final, and that would be if I stopped at 2 pi. Now this, I didn't specify that t needs to be between 0 and 2 pi, so this would just continue to grow and grow forever and ever. And we specified the direction, so I'm going to do that in a different color. Let's do that in blue. So this is continuing to move as time increases. This is my space curve, and it lies on this circular cylinder, okay, which also keeps growing, right, up and down forever. Okay. And you're not going to graph a lot of these by hand. You're going to do quite a bit of calculus with them, but a lot of the graphing we're going to do will be picture matching or looking at Calc-Plot3D just to see what these look like. But you can see that spiral pattern that's created. And so the main takeaway from this is since z equals t, the curve spirals upward as t increases around the cylinder. Around the cylinder as t increases. Okay. And this spiral around that cylinder, this space curve is known as a helix. Okay. Looks like a slinky. It's going to be one of the most popular examples that we come back to as we learn more concepts. We're going to use this helix and look at many different features of it throughout the semester and specifically throughout this chapter. Okay. On Calc-Plot3D, let's take a look at it here real quick. You have one drawn essentially already. In this case, notice the linear variable was t. I scaled it by 0.1 so you could see it on the screen. Otherwise, it would be, you wouldn't be able to see a lot of that slinky shape. So I just changed the coefficient so that it was dialed back a little bit. If I got rid of that, you would see it's growing in the y direction, but it's way too far off the screen. So I took the slinky and essentially compressed it so that you could see more of it. So the linear variable showing you the direction of motion, the cosine and sine components are showing you where that circular pattern lies. So in this case, the circular pattern lies in the xz plane for what I have on the screen. But the example we just did, the cosine and sine functions were x and y. So the circular pattern should lie in the xy plane. So let's change that. If I let it be t, you're not going to see too much of it. So I'm going to scale this back and make it 0.1 t so you can see more of it. And you could animate it again if you want to see the blue arrow, the blue vector tracing out. The tip of that vector is sketching out that space curve. Okay, so play around with it a little bit. What if you think about what would happen if you change this to like e to the t? Predict what would happen in terms of the rate of growth. Would it get slower, faster? Okay, let's watch it. Enter. Not surprising. It skyrockets very quickly up into the air at a certain point in time. You can animate that and watch that. There's your circular pattern. And then because of the rate of growth, it just all of a sudden takes off, right? Because of that exponential component in z. Okay, what if you made it parabolic? What would happen? Okay, now, if you zoom out a little bit, it almost looks like it starts crisscrossing. Okay, so a lot of different things can happen as you change that z component. But that nice steady rate of growth happens when you make it a linear component. Cool. Play around with some Calc-Plot3D if you want to see a little bit more of that. Okay, next up. Write or find a vector equation and parametric equations for the line segment that joins the point 1, -3, 4 to -5, 1, 7. We actually have done an example like this when we looked at writing equations of lines in vector form and in parametric form. If you remember, we pick a point to start at. In this case, we want to start, I'll start at A. You can start where you'd like. And we want to get to B. The way it works, my x of t, I'm going to start at 1, and then I'm going to look at the change, the direction vector that moves from A to B. So my direction vector in this case, v, would be the vector AB. And I'm going to subtract those endpoints component by component to figure out my direction vector. So -5 minus 1 would be -6. 1 minus -3 would be 4. 7 minus 4 would be 3. And so the x component is decreasing by 6 units. So this would be 1 minus 6t. Y of t, my y component starts at -3. It grows by 4 units plus 4t. And my z of t component starts at 4 and grows by 3 units as time increases. Okay, that would be the entire line. So if I was going to make this a vector valued function, I would just write it in component form. R of t would be 1 minus 6t, comma, -3 plus 4t, and the z component would be 4 plus 3t. They ask for a line segment, so we need to specify the parameters on t. In order for it to start at point A and end at point B, if you remember, t has to range between 0 to 1. You have to include that specification because it asks for the line segment. Okay, so this would be your vector valued function. And parametrically, still specify over here 0 is less than or equal to t, is less than or equal to 1. Okay, that would give you that line segment. Okay, find a vector function that represents the curve of intersection of the cylinder. There's our classic circular cylinder again, x squared plus y squared equals 1, graphed there in purple, being sliced by the plane y plus z equals 2. That's the plane that you see in green. If you slice that plane through that cylinder, it's not surprising to see that you end up getting an ellipse as the cross section because we're slicing on a diagonal through the cylinder. There is the trace or the intersection. So here's your cross section sketched over here on the right. That's this little curve of intersection right here. And we want to write an equation parametrically, and they ask for it in vector form. So we're going to come up with a vector valued function for that red curve of intersection. Looks like a rotated ellipse. Okay, so how do we do that? We use the two original curves to help us build that. And this is where your trig comes in. Makes the parametrizing a lot easier if you know your trig. X squared plus y squared equals 1. I'm going to start with that. I can easily parameterize just that projection in the xy plane. And if I think down to the xy plane here, there's my projection x squared plus y squared equals 1. When z is equal to 0, that's what I get. And even as I fix different values of z, I'm always going to end up with that specific curve, x squared plus y squared equals 1. And I know how to parameterize that. I could just let x be cosine of t and let y be sine of t. And if I let t range from 0 to 2 pi, then I've traversed the curve exactly once. So now how do I end up getting that z component involved in order to produce this red ellipse? That's where the height comes in. Well, that's where you can use the plane. You know what z is equal to. You can solve for this. Z is equal to 2 minus y. But we want everything in terms of the parameter t. So what is y equal to? Well, we said along that curve, y is equal to sine of t. So all I'm going to do is substitute in that expression for y. So z is going to equal 2 minus the sine of t. And now I have an expression for x, y, and z. Parametrically, I also am going to restrict t from 0 to 2 pi because otherwise we're just going to keep traversing this ellipse more than once. Typically, when you write the equation of the space curve, if it's a closed figure, you specify the parameter value so that it traverses that figure only once. Okay, so my parametrically, we have x is cosine t, y is sine of t, most popular parameterization for that circle with radius 1. And then in order to get that elliptical shape, z was equal to 2 minus y. So we get 2 minus sine t. 0 less than or equal to t less than or equal to 2 pi. They asked for a vector function. So I'm going to specify r of t. You can use ijk notation, standard basis vectors, or you can use component form. It does not matter. Cosine t, comma sine t, comma. This is what creates the space curve is that z component. where t ranges from 0 to 2 pi. Okay. And you can throw that into Calc Plot 3D if you want to see that. All right. All right, things you missed with T-Rex arms. How much have you missed limits? And how much have you missed continuity? It's been a long time. We're reuniting with some old friends. We're going to take a look at limits of vector valued functions, and we're going to ask ourselves if these vector valued functions are continuous. And this really just relies on the component functions. If you know how to take the limit of each of the component functions, and you know how to check continuity for each of the individual component functions, like you would have done last year in single variable calc, it's just a matter of putting it all together now. So it's a very, once you understand or once you recall how to do the individual components, you've pretty much evaluated the entire vector. Okay, so the limit of a vector value function R is defined by taking the limits of the component functions. So if I want to take the limit as t approaches a specific value a of that vector valued function, I'm just going to pass the limit operator through to each of my individual component functions. I'm going to take the limit as t approaches a of f of t, the limit as t approaches a of g of t, and the limit as t approaches a of h of t. And then I get my result. Notice the limit ends up being a vector. So the limit of that vector valued function is another vector of the three individual components. Provided those limits exist. We're not going to really look at examples where those blow up to infinity. Okay? We're going to look at examples typically where those limits exist. So that brings up the next point. How do we know if they are continuous? Okay. A vector valued function R is continuous at x equals a, or I'm sorry, at t equals a, if the limit as t approaches a of R of t is equal to the vector value function evaluated at the point t equals a. This should make you think, this looks very similar to how we defined continuity back in Calc 1 last year. So think about each of the individual component functions. How did you check last year if a function was continuous? Focus on one of those component functions. So a more useful way of thinking about this definition is that R is continuous at A if and only if the component functions f, g, and h are continuous at A. All of them. All three of them have to be continuous at A. So let's just look at it for f, and then it's going to be the exact same definition for g and h. How do I check to see if a function f is continuous at A? Three conditions. F of A, the function value at A, needs to be defined. Needs to be defined. Okay. Second condition, the limit as t approaches a of f of t needs to exist. Third condition, the value of that function needs to equal the value of that limit. So the limit as t approaches a of f of t needs to equal f of a. That is the third most important condition, because that's what makes everything come together for continuity. If that third condition is not satisfied, you do not have a continuous function. If you remember last year, you had some pictures like this. Maybe you had a hole, but then you had a function value above that hole. That's not a continuous. If this was a, the limit would exist. The limit would be approaching the y value of that hole. The function value would be at the filled in blue dot's height, but that function would not be continuous at t equals a, because the function value does not match the value of that limit. Okay? So that's one way it can fail. Now you have to check this for all three components. You have to check the continuity for f of t, for g of t, and for h of t. Okay? So let's look at an example. Part A, find the limit as t approaches 0 of this vector valued function r of t, where r of t is given by, I'm going to write this in component form, just because I like it better. T squared e to the t negative 2 cosine of pi t. Notice I picked nice continuous functions for this example. T squared is a parabola, e to the t is an exponential function, and we have a nice cosine function. It's reflected, it's stretched, and its period has been shortened, but it's a nice cosine wave. All of them are continuous functions. So we would expect this to be continuous, but we want to first find this limit. So all I'm going to do is I'm going to take the limit of each of the individual component functions. So the limit, I'm going to write out the notation for this one. The limit as t approaches 0 of r of t. Notice it is a vector, so I am putting my vector arrow above it. is going to be the limit as t approaches 0 of t squared, the limit as t approaches 0 of e to the t, and the limit as t approaches 0 of -2 cosine of pi t. And because these are nice continuous functions, I can just plug in 0 to each of the individual component functions and get my result. If I plug in 0 to the first component, 0 squared is 0. If I plug in 0 to the second function, e to the 0 is 1. And if I plug in 0 to the last component, the cosine of pi times 0 would be the cosine of 0, which is 1. And then I'm multiplying it by -2. -2 times 1 is -2. Okay. That's my limit. It's a vector. Okay. The limit as t approaches 0 approaches that vector 0, 1, -2. Is R continuous at t equals 0? Yes, in this case. Why? Because the component functions, f of t equals t squared, where do I have space to write? G of t equals e to the t, and h of t, define your functions. Nothing in the problem named them f, g, and h, so you need to specify that. -2 cosine of pi t are all continuous. Where? At that specific point at t equals 0. These functions are actually continuous everywhere, but I'm going to specify the point in question at t equals 0. Okay. All right, let's look at a more interesting example. What if there's some discontinuities? Okay, a little more work. Find the limit as t approaches 0 of r of t, where r of t is given by that specific space curve. Well, let's apply the same definition. Let's take the limit of the individual component functions. I'm going to let this one be my f of t. I'm going to let this one be my g of t. And I'm going to let this one be my h of t. And this one, I'm not going to write out the big giant vector of limits. I'm just going to go one by one. So for part 1, I'm going to take the limit as t approaches 0 of f of t. To be the limit, I'm just doing them off to the side here. The limit as t approaches 0 of 4t cubed plus 3 over 3t cubed plus 1. Be careful. A lot of times people I've seen in the past are like, oh, it's 4/3, because they're thinking about that horizontal asymptote. Notice you're not taking a limit as t approaches infinity or as t approaches -infinity. We're not looking at end behavior. If I was looking as t approaches infinity or -infinity, yes, I would get 4/3, right? But I'm looking as t approaches 0. So all I'm doing is plugging in 0 to the top and bottom. And I end up getting 0 plus 3, 3 over 0 plus 1, which is 1. 3 divided by 1 is 3. So the first component is going to be 3 for my limit. Part 2. Limit as t approaches 0 of g of t would be the limit as t approaches 0 of 1 minus cosine t over t. I'm going to try direct substitution. It's always my first strategy with a limit. I would get 1 minus the cosine of 0. 1 minus 1, I'm not going to put an equal sign. I'll show you why in a second. Would give me 0. Divided by, okay, if I put in 0 in the bottom, I get 0 over 0. If you remember from last year, that is an indeterminate form. You should never connect those with an equality. No, please don't write equals 0 over 0. That is not the value of the limit. That is an indeterminate form. Whenever an indeterminate form pops up, this should make you think L'Hopital's rule. So I'm just going to put a little note off to the side. Our good friend L'Hopital. I'm going to link in the description box a great video that gives a review of L'Hopital's rule if you need it. There is a calculus channel called Calculus by Christie, and it has some really, really great examples from single variable calc of various topics that we're going to cover. So throughout the list of videos, I'm going to link specific videos from her channel that review some of those concepts from Calc 1. She gives a really awesome breakdown of those topics. So I will link that in the description box, the channel and the video. For now, the short version, L'Hopital's rule, if you end up getting 0 over 0, or if you end up getting infinity over infinity, those are all examples of indeterminate forms. What L'Hopital's rule says is we can take the limit as t approaches 0 of the ratio of the derivatives of those functions in the top and bottom. So if I take the derivative of 1 minus cosine t, the derivative of 1 would be 0. The derivative of negative cosine t would be positive sine t. The derivative of t would be 1. And by taking the ratio of those derivatives, I'm going to put a little LH here. I used L'Hopital's rule. Now I can plug in and direct substitution works. That's the benefit of L'Hopital's rule. If you do it enough times, once you stop getting an indeterminate form, you can actually use direct substitution. Sine of 0 is 0. 0 divided by 1 is 0. Okay. Third piece. Limit. Uh-oh. Pen is acting up. There we go. Limit as t approaches 0 of h of t. So I get limit as t approaches 0 of natural log t plus 1 over t. Plugging in 0, I get natural log of 1. Okay, I'm not going to put an equal sign yet because it might be indeterminate. I get 0 divided by 0. Okay, it's another indeterminate form. Means we're going to use L'Hopital. I like to label LH above my equal sign when I'm doing L'Hopital. Something I was taught a long, long time ago in a math class far, far away when I took my calc class at U of I. Okay, so taking the derivative here, we'd have limit as t approaches 0. The derivative of natural log of t plus 1 would be 1 over t plus 1. And the derivative of t would be 1. So in this case, we can plug 0 in. We plug 0 into the top. We get 1 over 1, which is 1. And we have a 1 in the bottom. 1 divided by 1 is 1. So to sum up, to find this limit, this would be the first component, 3. This would be the second component, 0. And this would be the third component, 1. The limit of the individual component functions. So this limit, I'm going to go up to the top, as t approaches 0 of r of t equals first component, the limit was 3. Second component, the limit was 0. Third component, the limit was 1. That would be our limit. So the limit exists. Okay? The limit does exist. Now, the big question, is it continuous at t equals 0? Pause me and think about that for a minute. Okay. No, it's not continuous at t equals 0. Why not? Because the functions for g and h were not defined at t equals 0. The limits existed, but if I asked you what is g of 0, g of 0 is not defined. It was 0 over 0. Okay? That would not be a point on the graph. If I asked you what is h of 0, h of 0 also produced an indeterminate form. H of 0 produced 0 over 0. It's a hole on that graph. If I was to graph these individual functions for f, g, and h, I would have a hole at t equals 0 for both the g and h components. Okay, so no. I'm feeling 5 exclamation marks. Add more or less as you see fit. No. R is not continuous at t equals 0 because I'm going to define my functions. Even though I labeled them up top, I'm going to be more formal here. G of t equals 1 minus cosine t over t. And h of t equals natural log, I think it was natural log t plus 1 over t. Yeah, natural log t plus 1 over t. Are not defined. Where? They're defined in some places, but they're not defined at t equals 0. Okay? And again, this all goes back to that definition of continuity that you learned about last year. What's the first criteria to be continuous? F of a needs to be defined. Well, clearly, those functions, g and h, g of 0 and h of 0 are not defined values. Okay? So no. Okay? Even though f is fine, but it has to be all 3. Okay? So that sums up how to check for continuity and how to take limits of vector valued functions. You're probably wondering, can we take derivatives of these vector valued functions? Can we integrate these vector valued functions? And the answer is yes. But that's the sequel that you have to wait for until next time. Until then, happy homeworking, WebAssign, Packet, and happy mathing. See you in the next video.